Good day, students. Welcome to part one on AP Calculus AB exam review on free response questions. We're going to be taking a look at areas and volumes. That's our special focus today. All right. So we're going to be taking a look at the 2003 free response question on area and volume. All right. So this is question number one. It says, let R be the shaded region bounded by the graphs y equals the square root of x and y equals e to the negative 3x, and the vertical line x equals 1 as shown in the figure above. So this is a figure right here. This function on the top is y equals the square root of x, and this function on the bottom right here is the exponential function y equals e to the negative 3x. Okay? Alright, so this is a region that's being bounded by the two curves and this vertical line x equals 1. Alright? So let me indicate where the line is. This is x equals 1. For A, it says find the area of R. So let's go ahead and write down the formula for area. The area is basically we're going to use the formula, the integral from a to b. If we're orienting ourselves vertically, is going to be f of x, well, let's change the color. F of x, where f of x is a function on the top, so f of x, right on the top, minus the function on the bottom, let's call that g of x, so g of x at the bottom. Okay? If we're orienting ourselves using vertical rectangles. So this basically is the expression for the area of the region bounded by these two curves on the vertical line. All right. So note that the point of intersection here, if we trace it down, that will be our A. So we're going from A to B. So this would be our A right here, and that will be our B. Okay. So let's indicate those. This is A, and this is B. All right, so let's apply this function to this scenario. For part A, we're going to have our area, B, the integral from A to B. So the integral from A to B. So A to B are the boundaries of our vertical slice. So what is A and what is B? We know that B is 1, so we're going all the way to 1. So what is A? So A is basically the intersection of the two functions. All right, so A is basically the intersection of square root of x equals e to the negative 3x. So wherever they intersect, the x coordinate will be our A. All right, so let's go ahead and find that. We can use calculator for this part. There are two ways you can find the intersection. You can do it graphically, or you can do it from the home screen. If you're using the TI-89 titanium, you can use the solve function. You just simply press, let me make my calculator a bit bigger, F2, and then you want to solve this equation. So F2, option 1, solve the square root of x equals diamond e to the negative 3x. Solve that for what? What are we solving for? X, so comma x. So the syntax is after solve, you enter the equation and the variable that you're solving for. Close the parentheses, enter. Give it a second. And there goes the answer. It took a cool minute to find it though. Anyway, so that's the answer. So let's write it down. X is A, I'm sorry, A is where x is equal to 0.238734. Let's give it at 6 decimal places. We'll round up at the end, okay? So this solve function can be used for calculators that are TI-89 or TI-89 titanium versions. But if you don't have a TI-89 and you let's say you had a 84 or 83, all you simply do is you just go to the graph menu and enter the two functions. So let's enter the first function, square root of x close that, enter. And then the second one is e to the, where's the e? Make it bigger. So it's going to be, looks like my e has disappeared. Oh, let's see, there it goes. Okay, so e to the negative 3x, e to the negative 3x for your second function, enter. And you graph it. So that's the radical function, and there goes your exponential function. All right, so let's zoom in a little bit so that we can clearly see what's happening. I'm going to use a zoom box here, so I'm going to put my upper left vertex to the left there, and then my lower right vertex. Let's bring it a little bit beneath. So this would be my new window, so we can really see what's going on. All right, there goes the radical function, and there goes the exponential function. All right, so this is the intersection we're looking for here. To do that, we're going to use the math menu, F5, option 5. So it asks you what is the first curve. We could have 2 or more curves. So it wants to know the 2 that you're looking for, the intersection of. So press enter. That one is selected. Second curve, press enter. Now it says lower bound. Lower bound is the x coordinate to the left of the point of intersection. So that's the lower bound. See the arrow points to the right of the lower bound, or towards where the intersection is located. It says upper bound, scroll to the right of the intersection, enter, and there you have it. Okay, so you can see the x coordinate is what we need in this problem. So the beauty of doing this graphical approach is that it tells you both of them, whereas you're doing it from the home screen, it tells you only the x coordinate. Okay, so this method that we just used is universal for all graphing calculators. All right, now that we have the intersection, we're good to compute the area. We're going to set it up and use a calculator to compute it. So A is basically 0.238734. And then we're going to put in our functions. Parentheses, f of x is the function on the top, which is the square. All right, so it's the square root of x minus the function on the bottom, which is the exponential function e to the negative 3x. Let's close that, dx. And then I'll plug that in our calculator. Let's see what we get if we evaluate this integral. So plug that in our calculator. We'll have, let's go to the home screen. We want to compute the integral of the square root of x, square root of x minus the exponential function, e to the 3x, I'm on e to the negative 3x, close that, for x, and then the limits are going to go from 0.238734 all the way to 1. Okay, close that, enter. All right, so what just happened here? Okay, there you have your integral. So look at it closely. You have to make sure that your expression is consistent with what you have here. So going from 238,734 to 1. Good, that's what we have here in our pretty print. Root x minus e to the negative root 3x dx, and that's it. All right, so that's that. So let's write down our answers, and then we're going to take a look at a visualization. For our result, we can round it to 3 decimal places, so 0.44314. will work. Okay, so 0.443 is our area, 0.443. Alright, so let's take a look at this visualization. This is a graph of this situation right here. This intersection is 0.238734. So if we do the animation, that is what we just found. That's the area between the two curves. So 0.443 is your answer. Alright, so for the B part, we are to find the volume when the, scroll up, find the volume when the solid is when this region is rotated about y equals +1. So let's make a sketch of the situation here. So what we have is, for number 2, we want to find the volume when the given region that we had, I'm going to make it a little bit small here, that region is rotated about the horizontal line y equals 1. So let's say this is a graph right here. Okay, so the question is, can you visualize what it's going to look like? So this is the line y equals 1. This region is going to be rotated around that line. Okay, so you're rotating it about the line y equals 1. So what you want to note here for our formula selection, note that 1 is greater than the function on the top, f of x, and f of x is greater than the function on the bottom, which is g of x. Now what I want you to note is that this is important. We went over this in my other tutorial when I went over the formulas for finding solids due to revolution of regions. So if this formula doesn't make sense, you might want to go over that tutorial. I go over how to generate this formula in depth there. Alright, so I'm just going to directly apply it here. So to find the area, the volume of the solid, we know what the formula is the integral from a to b of the radius, the outer radius square, I mean pi times that, pi r square, outer radius square, minus inner radius square, dx. So pi times the outer radius square is the area of the outer disk, and then pi times the inner radius square is the area of the inner disk. And then when you compute the difference, that gives you the area of the resulting washer here. Okay? So in this problem, we're going to be integrating from 0.238734 all the way to 1. Okay? Pi times, we're going to be computing the outer radius is simply going to be what you get when you subtract 1 from the function that's farthest from the axis of rotation. That's g of x. 1 minus g of x. Put that in there. G of x. Okay? So that quantity square, this is the outer radius. Okay? Minus, to get the inner radius, we're going to do 1 minus the inner function, the function that's closer to the axis of rotation, which is f of x. Okay? Quantity square, that's your inner radius dx. So this is basically this formulaic setup. Alright, so let's apply this formula to the function that we're dealing with. So it's going to be, we're going to have the integral from 0.238734 to 1. We can factor out the pi, okay, times 1 minus g of x. G of x is a function that's farther away from the axis of rotation, which is e to the negative 3x. E to the negative 3x, that square. What we have just found is the area of the outer disk. Okay, pi times this square will be the area of the outer disk, minus the area of the inner disk, which is going to be 1 minus the inner function, which is a function closer to the axis of rotation, and that is our radical function, root x, so 1 minus root x quantity square, all right, dx. And then we just simply plug this into our calculator, and then when we do that, we're going to get an answer of 1.423. Okay, so I didn't go in depth as to how to generate this because I went over this in another tutorial, and that if you go over that one, it really helps you to understand how to come up with this setup. All right, so let's give ourselves a visualization as to what this solid looks like. All right, so there goes the two functions. So what we're going to do is take a look at that region and then rotate it about the line y equals x, and that's the resultant solid that you have. Okay, something like that. All right, and then when you find the infinite sum of all the washers on that domain from 0.238734 all the way to 1, you get the numerical value of 1.424. Okay, so that's the answer for part. And then for part C, it says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a rectangle whose height is 5 times the length of its base region R. Find the volume of the solid. So we went over this formula also in the other tutorial that I'm talking about. So I'm gonna include the tutorial in beneath the screen here, so you can just click on it for direct access. But in this video, I'm just going to go over how to create the formula. I'm not going in depth into it. All right. So what I'm going to do is I'm going to rotate my coordinate system in such a way that I can illustrate the depth of the function. So let's rotate our y-axis downwards, and that's our x-axis. Okay, and then we have two functions. Okay, let me shift this down a little bit so I can make enough room for my sketch here. So we have the two functions. We have the lower function, which is the function underneath is a exponential function. So it looks something like that. And then we have the function above, which is the radical function, something like this. All right, let me draw that again. So it goes from the origin and then something like that. Okay, and then we have that line y equals x. Well, I meant to say the line x equals 1. Okay, so that goes the vertical line x equals 1. That goes the function on the top, the function on the bottom. So we have a situation where we have the cross section is given by a rectangle. The base is 1/5 the height. And this cross section is basically the base of that rectangle. Okay, so let's go ahead and draw just one of the rectangles, and I will show you an animation of what it actually looks like. All right, so this is the base of the rectangle right here. This is one case. Okay, so this cross section right here is the base of a rectangle where the base is 1/5 of the height, or the height is 5 times the base. Okay, so let's draw the rectangle, something like that. All right, so there goes the rectangle. We see it's perpendicular to the x-axis, and its base is the cross-section of the region. All right, so let's say the base is s. What would the height of the rectangle be? It's going to be 5s per the indication there. All right, so the formula for the volume of a solid with known cross-section is basically the integral from a to b of the area of the cross-sectional face dx. Okay, so in this case, let's figure out what the area of the face is. What's this? This is a of x. What on earth is that? It's the area of this rectangle. Okay, so we know that the area of a rectangle is length times width, or side times side. In this case, is side times 5, s times 5s, length times width, which is 5s squared. In terms of x, the base length of this rectangle is the lower function minus the upper function. Okay, so this is basically equal to 5 times s is the function on the top, which is the radical function, square root of x, minus the function on the bottom. minus the function on the bottom, which is the exponential function, e raised to the negative 3x. Okay, so that's basically the expression for the area of the face of this triangle right here. All right, so just remember that the function on the bottom, this piece right here, is e to the negative 3x, and then the function on the top, this function right here, is the square root of x. So to subtract both of them will be determining the base length of the rectangle. All right, and if you multiply that by 5, that'll give you the height. So let's not forget to square it. So that's the area of the face. So the volume is going to be the integral from the intersection point, which is 0.238734, all the way to 1 of 5 times the square root of x minus e to the negative 3x quantity square dx. So you plug that in your calculator, and your answer is going to be, let's see what the answer is. It's 1.554. So your answer is 1.554. That's your volume. All right, let's take a look at the visualization of this. So there goes the two regions again, bounded by the region bounded by the two functions. So if we rotate it and set it to the side, and then what we're going to do is we're going to draw that rectangle, this rectangle, and then you see the solid that's formed right there. Okay, 1.554 is the volume of the resultant solid. Okay, so note that the base of the rectangle is the difference of the two functions f minus g, and the height of the rectangle is 5 times that difference. Okay, and then this would be a resulting answer. So that's that. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to our channel so you can get updates to other cool clips such as this. And do subscribe to our channel. And more clips can be seen on mathconcept.com/calculus. Thanks again for watching, and